Hi everyone, this is video number 7 of the Regents Chemistry curriculum, and in this video you're going to be able, after watching this video, you're going to be able to produce desirable products by conducting different reactions. So we're going to talk about chemical reactions, the type of chemical reactions, the type of organic reactions, and the types of nuclear reactions. We're not going to dig too deep into the nuclear reactions, we're just going to mention them and explain a little bit about how to read them. Okay, let's get started. Here are some questions for you. See if you can identify which of the following statements is true, which of the following statements are false. Take a moment, pause the video. If you don't know the answers to these, it's okay. You should be able to answer these questions at the end of the video. Let's get started. Okay. Before we go into what type of chemical reactions are there, what type of organic, what type of nuclear, let's just talk about what a chemical change is. A chemical change results in the production of a new substance. So anytime you're creating a new substance, anytime you have a precipitate, anytime you have a gas produced, you have some kind of a chemical change that took place. So a precipitate, which means just a residue, really that's what it is. Let's say you mix two solutions together and eventually you just got something at the bottom. So you ask yourself, why do I have something at the bottom? That's an indicative of a chemical change. Also, let's say you mix two solutions together and all of a sudden you got some kind of a gas produced. You smell something. That's an example also of a chemical change. Bubbles, you see bubbles. That's a chemical change. Okay, so a chemical change will always almost result in the production of a new substance. All right. Now, we have chemical reactions, we have organic reactions, and we also have nuclear reactions. Okay? Let's start by talking about chemical reactions. Let's see. There are 4 major types of chemical reactions: synthesis, single replacement, double replacement, and decomposition. These are the 4 main types of chemical reactions. Now, let's talk about each one of those. Synthesis. Here's an example. Na plus chlorine, sodium plus chlorine gives you sodium chloride. All right, that's the synthesis reaction. You use the sodium metal with a chlorine gas to synthesize something new, and what you synthesized is table salt. So this is what I mean by creating a new substance. You use the silver piece of metal and you combined it with some gas in the air, and then that silver metal with that gas gave you a table salt or salt crystals. Okay. Next, single replacement reactions. Single replacement reactions, let's read. Okay. Here's an example. So, magnesium, Mg, combined with AgNO3. So let's rewrite this to make it clearer. Mg plus Ag. I'm not going to balance it now. But Mg plus AgNO3 yields MgNO3. Again, this is not balanced. Plus Ag. Okay, so let's see what happens here. Magnesium is more active is a positive ion, is a positive element. Well, when it mixes with a compound, it becomes a positive ion. And silver is also positive. Now, according to table J, going to the reference table, we're looking at table J. We see that magnesium is more active than silver. is much more active than silver. Because magnesium is a more active metal than silver, it is more likely going to come and replace silver. And what I mean by more active, it's more likely going to lose the electrons and attach to nonmetals. So going back here, magnesium will come and knock off silver and take its place. So you'll have MgNO3 as a new compound that you just created, and then Ag will come right off as a residue in this reaction, as a precipitate. You'll get silver at the bottom. It's not going to be all polished, but you're going to get silver at the bottom. Okay, so that's an example of a single replacement reaction. Usually starts with an element and starts with a compound, usually. Okay, moving on. Next, we have double replacement reactions, and that starts usually with two different compounds. Here's an example. You have the same AgNO3, the silver nitrate, that is combining with sodium chloride. And now what happens is, it's kind of like an even swap. This Na swaps positions with this Ag. So this comes to hang out with NO3, while this comes to hang out with Cl. So you end up with Ag hanging out with Cl plus Na hanging out with NO3. This is an example of a double replacement reactions, and that usually start with two compounds, in this case AgNO3 and NaCl. All right, moving on. Next, we have decomposition, and decomposition is really the opposite of synthesis. So if in synthesis you synthesize something new, in decomposition you broke down what you have into simpler substances. Here's an example. KClO3. KClO3 was one single compound. It starts usually with a single compound that breaks down into two different substances. So here we broke down into KCl and we broke down into O, oxygen. Okay. Next, we have electrolysis. This is not a type of chemical reactions. There are only 4 types of chemical reactions, 1, 2, 3, and 4. Now for electrolysis, it's just a separation technique. We talked about it in the second video when we talked about separation techniques. It uses electrical energy to generate a chemical change and decompose compounds. So for example, if you had H2O, the positive end of the battery will attract the oxygen, while the negative end of the battery will attract the hydrogen. And that's how you use electrolysis to split compounds or separate elements of compounds. Neutralization is just another type of a double replacement reaction. It simply just follows titration procedures, and we'll talk more about that when we get to acids and bases. So if you combine an acid from table K with a base from table L, you're going to get salt and water. And why is this a double replacement reaction? Because you're actually combining two compounds together. So here's table K. These are all compounds which are representing acids. So all of these are compounds. If you combine any of these compounds with bases from table L, you're going to have a double replacement reaction. In other words, what's going to end up happening is that the H, let's say you're combining HCl, so let's say with NaOH, so you're going to have HCl plus NaOH. So the H will swap the positions with the Na, double replacement reaction. And then you're going to have the table salt, NaCl, plus the water, HOH. Okay? Moving on. Now we're going to move on to organic reactions. So for organic reactions, there are so many of them. Let's get started. First one, addition. When an alkene, just a reminder, when we talked about organic when we talked about naming and writing organic formulas or organic compounds, we talked about what an alkene is. So here, let's just clean this up a little bit. Okay, alkene, ene ending, must have a double bond. So if I have this alkene, take this for an example, and I added a group 17 element to it, let's say bromine, what ends up happening is this double bond that's here, I'm going to highlight it in green, one of those bonds, let's just highlight only one of those bonds is going to break down and is going to free those electrons. So a bond connects two electrons together. So when you break down the bond, you're going to have two free electrons. So what you're going to end up what's going to end up happening here is that ethene compound is going to look like this. You still have the hydrogen, okay? But now you have a single bond between the carbons. You still have the hydrogens again, but now you're going to have a single bond, and here is where your electrons become free. And guess what's going to happen? That bromine, those two bromines, are going to come right in and going to attach themselves here and here. So you're going to have a bromine here and a bromine here. This is how addition reactions take place in organic chemistry. You must start with a double bonded carbon, some kind of an alkene, and you add a halogen to it, any group 17 element. All right, now for substitution, on the other hand, for substitution, there's no bond to break. If you break a bond, you're going to break the chain, so you can't really break a bond. Substitution must start with a saturated hydrocarbon. So in other words, it must start with an alkane. Saturated, single bonded saturated substitution. So here's an example. If I add a group 17 element to this, like let's say Br2, what ends up happening is one of these Brs will come and replace one of the H's. So you're going to end up with the same ethane, but now you're going to have a Br here, not an H, and that H is going to come right off and is going to attach to the other Br. So you end up with an HBr, okay, and then you're going to end up with one bromo ethane. So that's substitution. Okay, going back here, we talked about addition, we talked about substitution. Now let's talk about saponification. Saponification is when you start with a triglyceride. In other words, you start with a fat, okay, and you add a base to it, a base from table table L, sorry. You add a base to it, which is anything that ends in OH, usually, with the exception of NH3. Fat and a base gives you glycerol, which is really just an alcohol. You see the functional group OH, OH, OH. That's an alcohol, or you can write it as glycerol. And soap. That's the soap that you use to clean your hands. You'll recognize glycerols because it has 3 OHs. You just have to recognize these reactions, really. Nothing more, nothing less. Esterification. You can remember esterification by remembering when you go to the dentist and open your mouth, and let's say you didn't brush your teeth in the morning, you say ah, and then the dentist says ew. So here you have your alcohol and the acid. So here I have alcohol and an acid. The acid you get from table K. And then you're going to get your ester, E for ester, and then you're going to get your water. You know the functional group of an ester. You can look at table R to recognize, to know how to name and write and draw the structural formulas of organic compounds. The previous video talked a lot about that. Next, you have a polymerization reaction, and that's when you start with individual hydrocarbon chains, and you just add them together to make one long hydrocarbon chain. Okay, this just tells you that you started with a certain number of the CH hydrocarbon chain, and then you added them all together and you have just a whole bunch of hydrocarbon chains. So you started with 1, 2, 3 ethene in this case, so you would started with 3 C2H4, and then you ended up with just, here's your C2H4, here's your C2H4, here's your C2H4, and it just keeps on going, one long polymer. Cellulose and proteins are natural polymers, while nylon is an artificial polymer. Your book bags are usually made out of nylon. Next, fermentation. That's usually what we do at distilleries to create alcohol. We bring some sugar, add some yeast to it, and we're going to get an alcohol. Ethanol is an example of an alcohol. Ethanol is the same liquor that's present in is the same alcohol that's present in liquor. And then carbon dioxide. Next, you have combustion. That's when you have a hydrocarbon, such as this, any of these, and you add oxygens to them, and then you're going to get carbon dioxide always, and water in gaseous form. Gas, 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 gas. Okay, and that's pretty much it for organic reactions. All right, when we get to balancing, these combustion reactions usually take a little bit of time to balance, and they require a little bit of a trick. We'll teach you that later. Okay, next, nuclear reactions. Let's read it a little bit. Make sure you remember that. They're all going to release energy. They're all exothermic. Here's an example of a fission reaction. You have a uranium-235. You combine it with a neutron, and you're going to get a very unstable uranium-236, which eventually breaks down to krypton and barium and start releasing neutrons and a whole lot of energy. So that's fission. Remember the key word? Bombard. You bombard uranium with a neutron. So this doesn't happen naturally. You create this, therefore this will be considered artificial transmutation because you started with uranium and you ended with krypton and barium. So it's transmutation because you changed. Mutation means changing. So you changed uranium to krypton and barium. Artificial because you caused that to happen. It did not happen by itself. Uranium was bombarded with a neutron. Now fusion is actually a natural process, a very clean process that takes place in the sun. Let's read about it. Okay, very difficult. This is positive and this is positive. Like charges repel. So this one will go in that direction and that one will go in that direction. You have to force them to combine. You have to force them to combine together. And this would usually require a lot of energy. Energy as much as the energy present in stars and stars like our sun. But once you combine them, you'll create the helium gas. So hydrogen and helium are very light gases. As you actually go into higher elevations, we run out of oxygen eventually, and we just end up breathing hydrogen and helium. So when you go climb a mountain, remember, your oxygen is very heavy, so it'll stay at the bottom. And then if you keep on climbing, you're going to have less and less oxygen. You're going to end up just breathing nitrogen and helium. Well, you won't probably make it that far, but that's why this process usually happens in the stars. Actually, the combination of two hydrogens to create helium is the reason why our sun is still shining. Okay, so for nuclear reactions, mass, energy, and charge of all matter is conserved. So remember, for chemical reactions. For chemical reactions, mass, energy, and charge is always conserved. For nuclear, the mass is less in the products because the mass is converted to energy. The mass of the reactants is usually converted to energy. So you release a lot of energy in nuclear reactions. Here are some examples of artificial and natural transmutations. So here we have aluminum bombarded with helium. And we're changing the, so this is artificial already as it is. And we're changing the aluminum to phosphorus. So this clearly is transmutation. So this is artificial transmutation. How do you recognize this is a nuclear reaction? You'll see numbers at the bottom and numbers on top. Numbers at the bottom, numbers on top. The numbers on top represent the mass. The numbers at the bottom represent the atom number, or the number of protons. Since it's nuclear reactions, we're going to talk about the protons which are in the nucleus. Again here, mass is on top, and then the number of protons at the bottom, or the charge. Charges at the bottom, charges at the bottom, number of protons at the bottom, number of protons at the bottom. For natural transmutation, you won't see any bombardments taking place like you saw here. For natural transmutation, you'll see an element by itself, just on its own, solo, that decays and mutates and changes into a different element. So naturally, on its own, just decaying particles. Okay? The reason why this element will decay is because the number of neutrons that's in it do not equal the number of protons that are in its nucleus. So neutrons in the nucleus don't equal the protons in the nucleus. That's why this will decay. And you can calculate that to make sure. Remember, the mass of an atom is simply just the protons plus the neutrons. So in this case, the mass is 16. So your protons are the atom number. Protons are prisoners chained to the atom number. So your protons are 7. And therefore, your neutrons here are going to be 9. So the protons do not equal the neutrons, or neutrons don't equal the protons. So therefore, this will naturally decay on its own. Okay? Well, when we get to nuclear chemistry, we'll talk more about the different decay modes and so on. Now let's go back to the questions. See if you can answer these. Identify which statements are true and which statements are false.